This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right. Today's lecture is going to talk about sensors and actuators. We're going to focus mostly on sensors. Actuators is a whole another area where we start getting involved in physics, electromechanical models and such. So I'm going to give you a very brief model of a particular actuator, which is a motor. It's one of the most common actuators that are in embedded systems. But we're going to talk about sensors, and it's an area that's often glossed over, particularly when you talk to programmers who just love programming code and who write code that just assumes that the sensors are working, reporting meaningful data, etc. We'll find it's a bit trickier than that, and I'll give you some real-world examples as we go. I'm also going to forecast what you'll be doing in the workshops starting this Friday or next week if you are in Monday to Thursday classes. Okay, so reference is the textbook, Intro to Embedded Systems. If you don't have it, please get it online. Chapter 7. So, what's a sensor? Pretty easy. It's like the read operation from the physical world. Okay, it measures a physical quantity. Sounds trivial enough. We'll find out that that's a bit of a loaded statement. Physical quantity, what does measure mean, etc. And an actuator, if you haven't heard of that word before, it's the writing part, okay? It's the out to the physical world. So we modify a physical quantity. Typically, it'll be some sort of motor or something like that, something that moves, because we live in a world where stuff has to move, basically. So it could be a motor-based control system. So sensors and actuators are this bridge in embedded systems between the cyber part and the physical part. Okay, the physical part being what we want to interact with, and the cyber part being our algorithms, state machines, whatever you like, programs that actually do the computation. And so some examples of sensors. I mean, you'd be fairly familiar with some of these sensors, at least having used them just from a user perspective. We go from simple things such as switches, which give you like a binary sort of output, off or on, to more complex things which may give back data types which give you a lot more information and maybe in some fancy format. For instance, cameras, right? Immediately you're thinking the particular image format, resolution, bitrate, all that sort of stuff is important. On the right-hand side is our output to the physical world, and these are actuators. And as I said before, motors are the number one sort of actuator that we think of when we think of an embedded system or a cyber-physical system. But solenoids, which are sort of a very simple sort of moving actuator, it's more of an on-off sort of thing. LEDs, lasers, LCD and plasma displays, they can also be considered as an actuator, something that we can write to the physical world. Loudspeakers, switches, and even valves, which are making a bit of a comeback in some applications, believe it or not. So what are the issues here? We have modelling issues, and I've listed some of them here. Firstly, physical dynamics. Is your sensor capturing the necessary physical dynamics? Now, that's not a trivial question. Most models, actually every model that we deal with, is an abstraction of something, and it's a simplification. Okay, we are taking things that are continuous, infinite dimensional systems, and we're kind of dumbing them down to very simple systems of differential equations which neglect information. So there are dynamics that are maybe missing from the particular model, even from the physics equations you may go to get your model from. Those things may have inherent assumptions, etc. Noise. That's a fairly obvious one. We can always assume that sensors can be disturbed by noise. And we can sometimes put bounds on it. And if you've done maybe probability and random models or any sort of stochastic signal processing, you can model the noise in a particular way, Gaussian, etc. like that, and try and deal with it when it arises. Bias is something we'll talk about today, and this is something that is a big problem, a really big problem, in particular when we are looking at positioning systems. And we've all used GPS before. Bias can be a big problem in positioning systems that use GPS and additional information to work out where you are. This is an inherent part of the way sensors model data. Sampling. This is a big one as well, in particular with IoT stuff. So depending on sample rates, we may miss things. We may alias signals. This is a big problem as well. As I'll say later on, when we look at aliasing, a lot of IoT stuff now, the underlying sampling that goes on of those particular sensors, and think of any of these things as being maybe IoT sensors out there, a lot of that's hidden from you. Things just report back data. And if it's in internet form, if it's TCP/IP, then some of the timing information about that is lost, particularly, with how often those things are sampled. And a lot of IoT stuff, we don't have control over the sensor side, if you're using the IoT stuff, because you're just reported data and you have no control over sample rate. All right, interactions, okay, so interactions between sensors, coupling of things like that. Faults is also a huge one. Mission critical systems where there are people's lives at danger and faults occur, we may have to put redundancy in the embedded system, in particular with aircraft, that's the big one, or most other safety mechanisms. All right, so the example I like talking about are cars. Okay, we can think of embedded systems as these abstract things that live inside computers and stuff, but a car is a perfect example that gives you a taste of all of the different issues we have with sensors and actuators, and humans interacting with those as well. All right. So, as I said, you've all mildly aware of or sat in a car that has different arrays of sensors. And it's a very difficult problem to put all those sensors together. So firstly, if you're just looking at a car from above and you're looking at the ultrasonic or the radar parts, which are the orange and the blue bits, you have multiple sensors reporting at multiple sampling rates, reporting different information at different ranges that can be affected by different levels of noise and can themselves have faults. For instance, the simplest one is if you go and bump your front bumper and break one of the ultrasonic sensors on there, then there's a fault in the sensor. So there's less data available for the car in order to make decisions about things. And that's a really interesting problem. What does it do if one of those sensors is missing? What does it do with the data from the remaining sensors? Then you even get more complex systems. So in yellow up there, maybe camera-based systems or vision-based systems like lane departure warnings. So it's detecting the lines on the road, and if you veer, it gives you vibration on the steering wheel, and it's a really uncanny feeling if you've never felt it before. It kind of steers you back into the lane. No, I was disabled as soon as I get in the car with that stuff. But anyway, it's going to be taking off, very soon, all this stuff. So it's complex. The brains in this car have to deal with multiple sensors, multiple data formats, multiple sampling rates, and making decisions based on all of those things, and in a split second as well, with possible user override. Okay, so you also have to take into account the human as being part of the physical side of this system. It's amazing once you think about the complexity involved in this. We just take it for granted. So, just to give you an idea about this sort of level of sensors that are required in cars, particularly if we start moving to these automated, autonomous vehicles, we have sensors that range in cost, obviously, but in terms of what their function is. Going from radar, video, LiDAR. So LiDAR is a tough one. It normally has to sit on the roof because it uses an array that rotates to basically get a 360-degree view of the surrounds of the car. You have ultrasonic sensors for sort of short-range stuff, and then radar or the LiDAR for longer range, things like that. GPS, we'll talk a little bit about that. GPS is not just satellites, but it also can take into account data that's reported from the engine system or the telemetry from the car. So things like tachometer, gyroscopes, internal gyroscopes, that sort of stuff, to get dead reckoning, which we'll talk about a little bit later. All right, and then down the bottom there, that's our sort of cyber physical interface, the central computer. And notice the cost of that is interesting. The cost of that is specified in terms of percentage of the sensor cost. So obviously it scales with the more sensors you have, the more complex the computer is there. So I say this stuff's exciting, right? Autonomous vehicles, fusions of sensors, and all things can go wrong, and user input and all that, but it's not new. Here's a video from 20 years ago. Driverless cars. Well, there's actually someone sitting in them, but they are driving along autonomously and following very close. That would be actually tailgating, probably, in Australia. But 20 years ago, this technology existed, and you can see, yep, hands off the wheel. It's doing about 100 kilometres an hour. And this is 1990s technology. Okay, yeah, you've got a colour screen, I'm surprised, right? I lived through the 90s, I know what the 90s were like. And so they still had radar. They had the radar range finding on the front there. It's a very old style radar that the police used to carry. Hydraulic actuators, or actuators anyway, they're coupled to the mechanical system. Now we have drive-by-wire systems in a lot of vehicles. That's the array of computing power. It took up the whole boot. Obviously, we've got a bit better in terms of 20 years of technology to miniaturise a lot of this stuff. But this is not new, so this stuff has been around for some time. There's some sensors in the bottom here that can track the road and stuff like that. And as I said, that's pretty close, and these are coordinated vehicles that are obviously able to respond to a changing environment quicker than a human could. There's no way if that one of the front cars hit the brakes, I would be able to react quick enough in order to stop and not run in the back of it. But these cars can. There's no reaction time, essentially, no reaction time involved. Pretty cool, huh? This stuff's old technology. And so, whoa, sorry. So there are automated vehicles out there now. So this is an example of a snowplow that's semi-autonomous. It has a manual speed control, but you can see the guy is not being lazy. He's letting the steering actuate itself. So it's slow, and what it does is it hugs the guardrails. Okay, so there's a guardrail. It's in the US, so it's obviously on the other side of the road to what we have here, and it's clearing the snow off the edge of the road. Now, it's a tricky problem. You get too close to the guardrail and you start scraping stuff, and we're talking less than 10 centimetres you want to get. And you can't see the guardrail because it's covered in snow, and if you get too far away from it, you're not doing your job. So, how the heck does this machine do it? Okay, so there's the planned gap to get it down to a couple of centimetres or a few handful of centimetres. How on earth does it do that? What sensors do you think it's using to find that guardrail? Any ideas? Let's kill the sound of the snowplow. Any ideas? Ultrasound? Good. Ultrasound's a good idea. The issue is, what's wrong with ultrasound? Sometimes the sensors get clogged up, you can get reflections, spurious reflections. Snow, I'm not sure ultrasonic waves go through snow too well. How else can it be finding that guardrail? I heard the M word, magnetic. Yes, but not the guardrail itself. No, not the guardrail itself. What's it actually doing? Let's have a look underneath it. That looks like an awesome machine on the front there, right? Those cutting blades. Underneath it is a magnetometer. I hate that word, but it's a magnetometer. And it's a bar. And the idea is none of this fancy GPS and all this stuff. GPS is not accurate enough to get it down to a few inches of clearance. The idea is to embed in the road magnets. Now, magnets are great because they need no maintenance. They're not electromagnets, they're just magnets. No maintenance, cheap, and you can stud the road with these magnets. And this snowplow just uses a magnetometer, which we'll talk about in a minute, in order to get its positioning data. Okay, and it's such a slow-moving object that it's it's okay. The bandwidth of the sensors and stuff is okay to be able to get that sort of resolution. But interesting, such a simple solution, and it requires a bit of infrastructure, putting magnets in the road, but as I said, it requires no maintenance. And magnets, magnetic field still works okay through snow and moisture and such like that. Interesting. So there's the automatic steering, and there's a bit of training, making sure it doesn't go over the witches' hats. So, yeah, you can see that driving. It does look like it's going to hit them, but I don't think it does. So that's a very basic, simple sensor application, and it's not, as you would expect, that high tech. Indeed, the principle behind that goes back even before electricity was a thing, 1879. So it uses something called the Hall effect. And Hall effect sensors are ubiquitous in embedded systems. They're essentially, yeah, they're there to detect proximity, to count events, all sorts of stuff. And how does it work? So let's look at the big picture up here, big A picture. It's a bit hard to, it's a beautiful picture, but maybe it's a bit hard to work out what's going on. So you've got a magnetic field there, 2 poles of magnets, and a flat conductor. That's that rectangular thing in the middle. Now the idea is if we pump a current through that, if there's no magnetic field, and obviously there is a magnetic field, but if there's no magnetic field here, the electron flow would flow through the centre of the conductor, right? Pretty much right from here to there, right? The current path doesn't want to bend around as such, right? Current wants to find the path of least resistance or least inductance. Okay, so it wants to go straight. And in the presence of magnetic field, essentially you are bending the path of the electrons. Okay, you can do some fancy Maxwell's theorems and all that sort of stuff to that, but it's well known that it bends the path of the electrons. And so what you get is you get a different charge accumulation. If you take a slice through there, right, you've got more electrons on one side than the other. Remember, you're applying this current via some sort of battery, and you can then detect the relative size of the potential difference that's caused by that field. Okay, so that's how you can get a positioning. You can imagine that bar under there could be the flat conductor of a Hall effect thing, and the magnets in the road, basically you can, if you have sensors that can read the potential difference across that bar at various points, you can find out where the magnets are aligning, so you can get your position. Okay, if you're looking at this sort of top-down from the letter A downwards. Okay, very simple and used everywhere. So magnetometers are great things, and they're used in autonomous vehicles, some autonomous vehicles. But what's really taken off in terms of sensors for embedded systems are accelerometers. And the biggest use of accelerometers, well, actually, they're in phones now, but the biggest sort of widespread application of accelerometers before phones was in airbag systems in cars. Okay, so they're used for navigation, orientation, drop detection, image stabilization, right? If you have a decent digital SLR camera, right, and you are a bit shaky, it's using accelerometer, 3-axis accelerometer to stabilise the lens in order so you don't get blurry images. And airbag systems, as I said before, where you need to measure a sudden deceleration, and you've got to measure it quickly to deploy your airbags. So how does this system work here? Okay, so this bar here is attached to the object, if you like. So you can imagine this, the bumper of the car or something. It's not this big, obviously. And it has an internal spring system with damping as well. A bit more about that in a minute, with a movable mass. So obviously this spring can compress and extend with this mass on the end here. So it has a spring because acceleration, we need to sort of, we need to measure the displacement of the spring in order to get some sort of acceleration measurement. And it has a damper on it. If you've done mechanics before, we need damping because we don't want oscillation. Okay, so we want to make sure, typically it's an underdamped system. So we put a damper in there. Okay, you can think there's electrical analogues for this as well with underdamped systems. Okay, so no oscillation. Oh, sorry, I'll just say, I'll go back to here. So how do we measure the acceleration then? Well, as that square block there, sitting on the spring, moves up and down to deceleration or acceleration, what happens is the capacitance of this system changes, right? If you have a capacitive material or conductive materials here, you can essentially measure the capacitance change from parallel plates. Okay, they look a bit like parallel plates, and so you can translate that into a voltage, which gives you a What's that? Where is that coming from? It's not the computer, I just muted that. Now it's gone. Okay. All right, so you can measure the capacitance and translate that into a voltage, which gives you a representation of acceleration. I'll talk more about how you do that with an affine sensor model in a minute. So this is a beautiful animation of the mass damper spring system as it's undergoing, not acceleration or deceleration, but it's undergoing rotation. So you can understand that the spring will want to extend and provide a restoring force when it's in either, say, the upright position, that's when it's most obvious, like there, or when it's in the downward, it skipped it, in the downward position there when it's undergoing compression. Now, note, this accelerometer here is not undergoing an acceleration that would be useful, measurably useful, right? We're thinking accelerometer, we want to detect an airbag. We want to detect a rapid deceleration. What is this modelling here? This is modelling rotation, tilting. Okay, so gravitational force is pulling that square block, if you like, that statue spring down, and it's squishing it down when it's in the lower position. Okay, so the mass damper accelerometer is great because it can, with the compression and extension, the spring can measure acceleration or deceleration, but it's bad because damn gravitational force on Earth is going to be affecting the measurements. Okay, so the distance measurement you're going to get out of the displacement of the spring is also coupled to the Earth's gravitational field. And that's a bit of a pain, a little bit of a pain. The problem is, if we are just reading values from this sensor here, there is no way to tell, because if you can't track that the thing's rotating, you're just reading the values, there is no way of telling that the sensor is undergoing rotation or tilting, if you like, rather than deceleration, acceleration. So damn gravity. It can get you into trouble. So what we could do, what we could imagine is, actually, I wonder if I could, is that going to pause? Yeah. So what happens in free fall? And you're going to find this out when you do the first workshop. What happens in free fall? So if this is sitting here statically, maybe at this angle actually, let's pretend it's vertical, it's actually representing, it's actually measuring the gravitational pull of the Earth, right, in the z-axis, if you like, or the up-down axis if we want to live in 3D. In free fall, what happens? Well, objects become weightless, right, because, they're in free fall. So what would happen? Well, the spring would probably extend and the little block would go up, and we would measure zero acceleration in all three dimensions. So interestingly, devices that are mechanically, can be damaged mechanically, for instance, hard drives. So hard drives have a platter of discs with a head that's like a record player, if you like, very fine needle, and if you've ever given a physical shock to it, you can damage the surface of the disc. It's spinning at high revolutions, and it's a very fine needle-like arrangement, sometimes multiple, that can scratch the surface or damage it. So what happens? Typically, inside these hard drives, there's a 3-axis accelerometer. And when you drop that laptop with the hard drive, with the mechanical hard drive in it, your laptop, or the drive, can detect it's in free fall. Okay, so it's reading its accelerometers. It's going, whoa, I've got zero for everything. I'm in free fall in the 3 dimensions, right? What does it do? It parks the heads, basically. So this disc is spinning, and immediately it'll rip the right head or red head away from the spinning disc because it knows an impact is imminent, okay? If a laptop's in free fall, it's going to get a big shock very, very soon. And so That's how sudden motion sensors or shock sensors work in laptops, with mechanical hard drives in them anyway. Just disconnects the head if it detects heads if it detects freefall. So let's look at a model of a little accelerometer here. Let's lay it on its side. So let's pretend that the gravitational effect is not present anymore. And this level of maths / physics or something like this shouldn't be too much of a scary thing for you. Okay, so it has a restoring force, the spring, but it also has some damping involved, and the damping is proportional. The force of damping is proportional to the velocity of the object that's moving on the spring there. Okay, so you can crank it together and essentially get a second-order differential equation for the position x of the block here, right, relative to the fixed frame of the accelerometer here. And if you really want a bit of punishment, you can convert this equation to an integral equation, second order, so you can do some integration on here with some initial conditions. Okay, so this has no gravitational effect on here because we're assuming that gravity is not going to play. Gravity is acting vertically in this diagram, so it's not going to be affecting it in any which way. It becomes more complicated, obviously, once again, when we start rotating it, because gravity is now going to start affecting the restoring force of the spring, and it's going to be a bit confusing as to what's going on. Okay, so we can measure the tilt with an accelerometer, believe it or not. So most people think, well, accelerometer, I know if I've got that equation there, I can do this integration, solve this integral equation and get x, right? X is what I want, and then x will give me some sort of position measurement which I can relate to perhaps the movement of the object. But tilt can also be measured. So if we assume that this guy is not accelerating, but it's just stationary and it's rotating now, you can work out the proportion of the gravitational force that's acting on the spring there. Okay, so it's like it's an angled spring system. That's all it is there. And so with this system here, you can measure, if you can measure x through capacitance or some indirect measure, you can solve for the angle theta. And there's a bit of ambiguity. You basically get up to an ambiguity of pi in radians here because you can't tell, obviously, how it's been tilted. Okay, so in next week's workshop, or this week if you're on Friday, you'll be interfacing with, and I brought one with me just to show you, one of these guys here. So this is I'll give you some lights to flash. This is a Nintendo Wii Mote. Okay, so for those of you who ever had a Nintendo Wii, these were fun back in the day. You could do all your movement-based stuff in there. And it has a 3-axis accelerometer in here, so it can detect movement, which is fantastic. So you guys will be interfacing this and reading the sensor data back on a computer. And you'll notice, if you place it flat, leave it there, one of the axes of acceleration will be reading g, right? Because it's if you think of our little model with our spring here, right, it's measuring the acceleration of the Earth, trying to pull this thing down into it. Okay, and we can tilt it, etc., and read all the 3 different axes of acceleration. Now, using something like this to get your position then, okay, that's easy. We can get our position from this. The problem is it's very difficult, once again, to separate tilt from an actual acceleration. Indeed, if you're good with physics and can flip yourself into different reference frames and things like that, it makes more sense not being able to distinguish a tilt from acceleration because of damn gravity. We also have vibrational issues as well. Okay, so if there's vibrations, it may not necessarily be detecting a an acceleration that we want in terms of the movement of the sensor, but it's noise, essentially, and non-linearities in the spring or damper. The last issue that we have, and the reason why the accelerometer is not used in this for position-based measurements, is drift, sensor drift. So why is this not a very good tracker? It's got a 3-axis accelerometer. I can assume I start at velocity 0, and if I start moving along, I can measure the acceleration. So by integrating some equations, I should be able to find my position, right? I should know where this thing is at all times, because if I know a starting point, perhaps. No. The accelerometer in this thing is only used for tilt measurements, interestingly enough. Just getting that, working out what angle it's on, not its acceleration in order to work out its position in space, position, like XY position, right? Just in terms of its angle of operation. How does it do that? How does it do position in space? There's actually a little window on the front here with an IR camera, if you like, which with a bar on the unit can detect where it is according to that. So it's a vision-based system to work out where its position in space is, and a 3-axis accelerometer to work out what angle it's on. Interesting. So the problem is with drift is we all know from solving too many of these damn physics problems that remember x is some measurement which could be obtained by, say, capacitance. But if we get I think I see an error. If we get a measurement of the acceleration somehow, so x double dot, okay, x double dot, that should be, we can integrate that acceleration to get velocity with an initial condition, and we can integrate the velocity to get position. Problem is that if there's any bias in this measurement, and we'll talk about bias in a minute, a double integration is going to cause essentially a quadratic position error. And this is what's known as drift. Okay, so just a little bit of bias in this measurement here from a sensor, integrated and integrated again gives us a quadratic growth in terms of our position is, the error is growing quadratically, which is bad, right? We don't like those sorts of growth in terms of error. How do we counter that? We'll talk about that in a minute. So how do you measure orientation? If measuring the tilt of something's difficult using accelerometers, you can use a gyroscope. And here's a beautiful model of a gyroscope. And these were used in ships and things like that, aeroplanes, old aeroplanes, a real physical model of a gyroscope, something spinning with a double gimbal attachment to it. So if you've ever seen the physics experiment or done it yourself where you spin a wheel and it has a small axle through it and you spin it this way and you try and rotate it, right, it's very difficult to move it off its axis, okay, due to some sort of physics principle, conservation of angular momentum or something like that, right, but it's very difficult for it to move. So what you can do is if you have a spinning disc on an axle inside this double gimbal here, so it's the gimbal on the outside is freely rotatable in both dimensions there, you can determine your rotation if you imagine you're sitting on this outer ring. So instead of imagining that disc that's spinning is immovable, right, imagine you're on the actual outer ring and you're stationary, but the spinning disc is the thing that's moving, okay? And by taking measurements of the relative movement of this, you can work out what your orientation is. I won't go too much into this, but this is the old school gyroscope. Now they use lasers and interference patterns. So you basically send laser around two different paths through a half silvered mirror, get an interference pattern. You can work out the path difference that the light's travelled and such, and work out that it's been rotated. So this is the more miniature sort of version of a gyroscope. Okay, so that's how you can measure your change in orientation. So a lot of embedded systems have inertial navigation systems in particular, right? Cars that have tracking on them and such like that, aeroplanes. So what is an inertial navigation system? It's essentially, it's called dead reckoning plus GPS. And I'll give you just a funny anecdote. Dead reckoning is actually spelled D-E-D. Dead reckoning. And where did that word come from? It actually came from, it's short from the word deduced, which doesn't have an A in it. Deduced. Deduced reckoning, right? You can deduce what your position is based on sensor data. What happened was, somewhere along the line, this became dead. So, but there's nothing dead about it. Okay, so when we talk about dead reckoning, it's actually should really be deduced reckoning, funnily enough. Okay, so GPS, it's great. We all have it on our phones and navigation systems of cars, but it's not that great because it's not super accurate, particularly for localization purposes down to, you know, we're talking inches or something like that. So the idea is we can combine 3 different sensor values. GPS, to get some sort of initialization, initial fix, and then get periodic correction to fix the problems inherent with the other sensors. Use a 3-axis gyroscope to get your orientation, because that's important, right? Which way you're facing, the angle that you're on, well, in the 3 dimensions, the 3 angles. And also a 3-axis accelerometer, which can then, as we know, be double integrated for position after we correct for the orientation. Okay, so you need to know particularly the orientation and the acceleration in order to be able to predict where your final point may lie. Now, so with the sensor drift problem, right, we know that the accelerometer, if you're double integrating this guy, this sensor drift is giving you quadratic errors. That's easy. We can then periodically go to GPS to grab a fix and then reconcile the 2 together and say, well, you know, maybe I'll scrub some of this, the data that's coming from this. Okay, so, and GPS doesn't update very often as well. It's at the order of hertz in terms of updates. Okay, so aircraft have small amounts of drift, but they can be corrected by periodic GPS updates. Is it good enough? I hope so. Right? Next time you're on a plane, hopefully their GPS updates account for the drift properly. Okay, so another type of sensor, we won't talk too much about this, is a strain gauge, for instance, if you're into civil sort of stuff or you want to look instrumentation of civil. So it's a mechanical gauge. You bolt it rigidly to the thing you're measuring and it can detect the deflection. Well, it detects deflection, which detects movement in things. So that's the old school visual way of doing it. You look at the way that the bars have moved over time, and you can do it with an electrical system. If you put a current through some sort of array, that under tension or compression, its resistance changes, essentially. Okay, I won't talk too much about the strain gauges here. So what's the problem with sensors? Once again, this is something you probably haven't thought about. Calibration is a big problem. So, as we'll see, I'll show you a data sheet that no 2 sensors are generally alike, for a reasonable cost anyway, in that they report different things. So, firstly, if you need to calibrate sensors, it immediately adds heaps to the manufacturing costs. Normally by calibration, it involves someone sitting there with a plastic screwdriver, tuning some potentiometers in a circuit. Maybe not for miniature circuits, but for amplifiers and things like that, that's what it needs. And how it relates to the actual physical phenomenon you're measuring. The good old non-linearity. We like our sensors to have a linear or an affine relationship, as I'll say in a minute. Problem is that nonlinear sensors may have regions where that's true, but outside of those regions it's bad, right? It's a nonlinear relationship. So we may need to correct those by some sort of mathematical trickery to undo the nonlinearity, or use feedback to try and keep the sensors within the linear range. Okay, and there's plenty of nonlinear sensors out there that we try and tame by feedback control. Sampling. As soon as we get into the cyber world of stuff, we have problems with sampling. Aliasing, which I'll talk about, missed events if we don't sample things fast enough. Noise, that's an obvious one. We may need to use analog signal conditioning, so SIGPRO, that sort of stuff, digital filtering, and there's also latency involved if you're using FIRs and some things like that. And then lastly, what do you do when a sensor fails? Okay, redundancy. You need some sort of algorithm that fuses the sensor data and has a plan when one of those sensors either reports a value out of range, doesn't report, whatever, because it's damaged or something, okay? And then also security, and we'll talk a little bit about security towards the end of the subject here. Can sensors be spoofed? Can they be attacked by a bad actor? Okay, so I want to talk about the affine sensor model because that's what you're going to be using in the workshops next week. And bias and sensitivity, and they're the two elements of the affine model. And in particular, I want to look at the particular analog device's 3-axis accelerometer datasheet. So what's the affine sensor model? I'm going to give you a formal definition of it. It's very important to formalise things, particularly when we're dealing with life-critical systems, okay? We're not hackers. If you want to be a hacker, you go to an electronics course at some other institution or whatever, throwing some stuff together. Here, being at Uni Melb, we need to be a bit more theoretical, not theoretical, but a bit more robust in the way that we define things, not just plugging stuff together and it works, so therefore it's all good. So the affine sensor model looks like this. Okay, so let's pretend X is a physical quantity. Let's think of that, maybe it's that displacement on the accelerometer, the spring system there. So X is a physical quantity. And we'll assume that X is a real number, okay? So it's just some value. So what does the sensor do? The sensor's a mapping, right? It takes that real value and maps it to something else. So the sensor is really a function, let's call it f, that maps R to R. Okay, let's assume that it maps it to a real number. And if it's an affine model, it has the following relationship. It's a mapping from that X, which is the real raw sensor data value, to a line with it's a first order line with a slope A and a intercept B. But we don't call them that. Maybe you do in maths, but we call this the sensitivity, and we call this the bias of the sensor. And as I said, this is non-trivial stuff that we have to think about here. You can't just take a given sensor value and just accept it. We need to know the mapping between the sensor value and what it spits out, between the measured quantity and what the sensor's reporting. So obviously this sensitivity here is just equal to the derivative of the function. Okay, so let's look how this plays out in a real-world sensor example. So, unfortunately, I've only got one screen here, which kind of sucks. So, I'm going to have to flash up some data sheet, and we'll get back to this. So, this is a 3-axis accelerometer. If you, analog devices one, if you pull the data sheet down, you can go and Google that if you really want. It tells you its typical operating conditions here, including measurement range, bit of non-linearity, at least it's small, and some of the offsets that are measured. Well, bias level, hey, that's the B part here. Okay, so it reads from minus 3.6G to plus 3.6G. And that's kind of probably, maybe that's about the range of someone who would be thrashing this thing around playing a game. It's probably of the order of, I don't know, 3G to minus 3G to plus 3G. And it works off a supply of 3 volts. Okay, so what this sensor does is, it's a mapping, right? We've got to think of this as a mapping. It maps a continuous range between minus 3.6G and plus 3.6G. So let's do this in units of G. And it maps it to a voltage. Now, if the supply is 3 volts, we've got to do the mapping this way. So this is the voltage readout. And it's in volts. So the way that this sensor works is it maps anything in that range to 0 to 3 volts. So put 0 there, 1.5 and 3 volts, assuming it's a 3 volt supply. So the mapping is clearly that minus 3.6G becomes 0, 0 becomes 1.5, and 3.6 becomes 3, assuming an affine model for this. So we're going to assume that this mapping is fx, is ax plus b. Oops, forgot my variable there. And we can determine both a and b clearly from looking at these relationships here. Well, obviously, if we're mapping from here to here, and this is the mapping, then my bias is 1.5 volts. Okay, so that's the bias of the sensor. Volts, I should there. And lastly, well, what's AA is the sensitivity of my sensor here, and that is the gradient. So if we're talking about, we could talk about a range of 3 over 7.2 or 1.5 over 3.6. Doesn't really matter. So I'm going to say it goes 1.5 to 3 over 0 to 3.6. That'll do. So its sensitivity, and these are, the units will be in volts per G, is 0.417 volts per G. And so if you end up finally mapping this to a digital value via an AD conversion, let's say it's a 16-bit AD conversion that takes place of these values here, then this would represent 0. We use positive voltage, positive values here, and this represents 65535, something like that, with the midpoint being 32768. Okay, so this is what we would end up with in our good old little C program, that we would then be making decisions based on these values here, right, this raw 16-bit number here, which we have to backwards engineer in order to get the real G value. Now, you in the workshops are going to be measuring the bias and the sensitivity of your little Wiimote in order to make more accurate readings of the data. Okay, if you don't take into account the A and the B parameters in that affine model, you won't get meaningful data out of it. Okay, we'll leave it there. We'll talk a bit more about sensors next lecture, and then I'll start talking about embedded processors and the different families of them, pipelining, parallelism, etc.
问。
Yeah.
哇，你怎么上这课啊？
Legit, this